Section 2.4 talks about continuity. So one of the things we're going to be talking about here, y'all, excuse me, we're going to talk about three conditions for a function to be continuous at a point. We're going to talk about three kinds of discontinuities. We're going to talk about continuity over an interval. We're going to talk about a theorem for limits of composite functions and an example of something called the intermediate value theorem. Okay, so let's take a look here. I'm going to kind of scroll down here. Continuity at a point. So it says, before we look at a formal definition for what it means for a function to be continuous at a point, let's consider various functions that fail to meet our intuitive notion of what it means to be continuous at a point. Then we're going to create a list of conditions that prevent such failures. So here's our first function. And it says we're looking at the graph of f of x, and it has a hole at the value when x is equal to a. Let me get my pen going. Here we go. So you can see at a, we have a hole right here in the function. And so f of a is undefined. And so for the very least, for f of x to be continuous, we need the function to be defined at that particular point. Okay, so... and then it says in figure 2.33, which is the next picture coming up, it says this condition alone is insufficient to guarantee continuity at a point. Although f of a is defined, the function has a gap. So let's take a look. Oh yeah, I don't know why it kind of had this big gap here in terms of the notes, but here we go. So our function is not continuous at this point because we have this gap, right? As I take the limit as I approach from the left and the limit as I approach from the right, you can see they're not the same. So the limit doesn't exist, right? Okay, so even that's not enough. You can see here that the limit exists as we come from the left and the right, and it's the same limit, so we know in general the limit exists, and the function is defined because we have that solid point right there. But it's still not continuous. So a lot of times the way we kind of describe what does it mean for a function to be continuous at a particular point, we should be able to draw the graph without having to take our pencil off the paper. That's basically the easiest way to kind of describe this. So if you're noticing here, we kind of have to stop. We got to fill that point in, come back, do something like this, right? Here we stop, and then we have to kind of jump over, put that open circle. I'm having to take my pencil off the paper, right? And even this one here, I'm coming in, and then I have to stop, jump over, and do that. So like intuitively or informally, a function is to be continuous if you can draw the graph without having to take your pencil off of paper. Okay, so let's take a look here. Here's the formal definition. So the definition says a function is continuous at a point A if and only if the following three conditions are satisfied. So number one, the function is defined at that particular value. And number two, the limit exists. Remember what it means for the limit to exist. The limit from the left has to exist. The limit from the right has to exist. And then they have to be the same. And then the third one says the limit as x approaches a of f of x has to be the same thing as if when you evaluate it at a. So you need all three things in order for the function to be continuous at a particular point. And it says it's discontinuous if it fails to be continuous. So if it doesn't meet any of those criteria, it's going to be discontinuous. So it says the following procedure can be used to analyze the continuity of a function at a point using this definition. Oops. All right, here we go. So number one, we're going to see if it's defined at that particular value. If it's undefined, we don't need to go any further. We can say the function is not continuous. Okay. If it is defined, then we're going to find the limit as x approaches a. Sometimes we got to look at the limit from the left and the limit from the right, make sure it exists. And if it doesn't, then we're done, right? It's not continuous. And then the third one is that the function evaluated at that particular value has to be the same thing as the limit. And if they're the same, then we're good. If we're not, then it's not continuous, okay? So let's take a look here. Determining continuity at a point. It says use the definition to determine whether the function f of x is equal to x squared minus 4 over x minus 2 is continuous. So the first thing we're going to do is we're going to evaluate f of 2. So when we plug in 2 into here, y'all, so 2 squared is 4. Oops. And on the bottom, we have 2 minus 2. So we're going to have 0 over 0. This is indeterminate. It's undefined. We can't do it. Okay. And so it is discontinuous because f of 2 is undefined, right? And you can see from the picture, this here would be at 2. And you can see that, you know, we have that hole in the graph, okay? Let's take a look at the next one. So determining continuity at a point, second condition. Remember what we're trying to do. So the first thing we want to know is the function continuous at, say, 3? So we're going to find f of 3, okay? So to find f of 3, since this is a piecewise function, I am going to use the top part because the top part says when x is smaller than or equal to 3, then we use the top part. So we're going to go negative 3 squared plus 4. This is negative 9 plus 4, which is negative 5. You can see right there. Okay, now we want to find the limit. Okay, so remember, if we're going to find the limit, we're going to have to take the limit as x approaches 3 from the left. Oops, keep wanting to write it, put a negative 1, it's just a minus sign. Okay, so that means we're going to evaluate the limit right here. So we did that actually by evaluating it. That was equal to negative 5. Now I'm going to find the limit as x approaches 3 from the right, which means I'm going to use the bottom part because I'm picking numbers that are slightly larger than 3, right? We're still going to evaluate it at. So let's see, we have 4 times 3 minus 8. This is 12 minus 8, which is 4. You can see that my limit from the left and my limit from the right do exist, but the limit itself doesn't exist because those two values are different, right? So the limit as x approaches 3 does not exist, and that's why our function is not continuous. So you can see here is the picture, y'all. This is what the picture looks like. And you can see that, again, if I was drawing my graph, I would do this number, and I would put a solid point, but then I got to take my pencil off the paper and do that, right? Okay. And so the last part here says, use the definition to determine if the graph is continuous at this particular point, which is x equals 0, okay? So here is, let's see, here is our graph, right? So here, this graph here, y'all, what this graph is the sine of x is over x, right? So that's why I have that. Now, I want you to notice what happens if x is equal to 0. We're going to fill this thing here at 1. And so does the limit exist? So if I come in from the left and if I come in from the right, the limit is equal to 1, right? Is the function defined at 1? Yes, it is. It is equal to 1 itself. And are the limits and the function evaluated at that point the same? Yes, so this function would be continuous at x is equal to 0. Okay. Let's see, continuity of rational functions. So remember what a rational function is, y'all? Rational functions are basically fractions, right? And it's asking me, for what values of x is f of x is equal to x plus 1 over x minus 5 continuous? So when we have a fraction means we're dividing. The one number we cannot divide by is 0. So if we set the bottom part equal to 0 and solve for x, we can say that this thing is continuous for all real numbers except for x is equal to 0. So what that looks like on the number line, y'all, if this is my x-axis, we are going to remove when x is equal to 0. So in interval form, it would be from negative infinity to infinity, and then we're going to skip over 0 and go from 0 to infinity. Okay? Not 0, sorry. I meant 5. Sorry, guys. So we're going to say this number here was 5, not 0. Okay, there we go. And let me fix these intervals too. That was my bad, y'all. So let's fix this to 5. And there we go. Okay, we want to pick every number except for 5 because 5 makes the bottom part equal to 0. Okay. Alrighty. So types of discontinuities. So we have something called a removable continuity or discontinuity. A removable discontinuity is when you have like this missing point. Okay, that's what we call a removable discontinuity. This is called a jump discontinuity because you can see in order to do this, I have to jump from this point over here to this point. And then we have something called an infinite discontinuity where when we take the limit as x approaches whatever particular value, a that is, from the left to the right, it's either going towards positive infinity or it's going towards negative infinity, okay? By the way, y'all, this graph here could also look something like say here's my number a. It could also look something like this, where it's coming in and it's going down that way, and it's coming in and doing, something like that. It doesn't have to be approaching positive infinity from the left. It has to approach one of the two, okay? So let's see. Here's like the formal definition. It says f of x is discontinuous at a, then f has a removable discontinuity at a, so the limit as x approaches a exists. Note when we say the limit exists, we know that the limit as x approaches a of f of x is equal to L, right? So the limit's going to exist, but we have that removable point, okay? Jump discontinuity means that you have a limit as a approaches, as your x approaches a from the left, and you have a limit as x approaches a from the right. They're both going to be limits, but they're different, okay? So that's what's kind of going on here, right? As I'm approaching from the left, we have a particular value. If I'm approaching from the right, we have a particular value, but they're different. So the limit doesn't exist, but the limit from the left and the right do exist. And here we go. So the infinite discontinuity, that's what we were talking about earlier. Whereas you're approaching your value, let me come back over here so we can look at the picture. As I'm approaching my value of a, I'm either going towards infinity or I'm going towards negative infinity, okay? And again, the same thing can happen whether you're coming from the left or the right, okay? That's what we mean by infinite discontinuity. Okay, so now it says, we showed in example 2.26 that the graph was discontinuous at x equals 2. Classify this discontinuity as removable, jump, or infinite. So look, the easiest way to do this, again, you could always look at the picture, but if you factor the numerator into x minus 2 and x plus 2, and now we say, look, we're going to go ahead and cancel these common factors. What did we do? We removed the common factor, right? So this would be a removable discontinuity, okay? Because we removed that common factor, okay? I hope that kind of makes sense. All right, so now, same thing here. We want to know if the function is, since the function is discontinuous, is this removable, jump, or infinite? So again, look, we're going to do this right here, y'all. Let me get my pen working. Sometimes it freezes on me. Here we go. We're going to take the limit as x approaches 3. We're going to take the limit from the left. So again, we're going to use this top part of the function of negative x squared plus 4, which was negative 3 squared plus 4. Negative 9 plus 4 was negative 5. And then if we find the limit as x approaches 3 from the right, excuse me, we're going to use this part of the function, the 4x minus 8, which is 4 times 3 minus 8. 12 minus 8 is 4. So since the limit from the left exists and the limit from the right exists, but they're two different limits, the limit in general doesn't exist, this is what we call a jump discontinuity, okay? Because you're having to jump from y equals negative 5 to y equals positive 4, okay? There's a big jump there. Alrighty, So now let's take a look at this next one here. We're going to classify whether f of x, which is equal to x plus 2 over x plus 1, is continuous at x equals -1. And if it's discontinuous, classify it. Okay, so first thing is, is it continuous or not? So the first thing is we have to ask ourselves, can we find f of -1? Is f of -1 defined? So this would give me -1 plus 2 over -1 plus 1. This is 1 over 0. This is clearly undefined. So we already know it's discontinuous. We're trying to determine, is it removable, is it a jump, or is it an infinite? So a couple of ways we can do this, right? We already know it's undefined. The first thing I'm going to do here, y'all, let me get my calculator going. Let me clear this out. I'm going to go to my y equals. I'm going to leave the other ones there. I'm just going to enter in this new one. So this is going to be x plus 2. I'm actually going to put this in parentheses because it's a whole expression, right? Divided by x plus 1. There we go. Enter that in. Okay, so let's quit this. Let's go to vars. Excuse me, let's go to vars. And I'm going to evaluate my function. I'm going to take the limit here, y'all, as x approaches -1. I'm going to take the limit of the as we're approaching from the left, okay? So what does that mean I'm going to do? I'm going to take numbers that are slightly smaller than -1. So again, I'm just going to kind of do a visual here for y'all so you can see what I'm looking at. So here's my graph, right? Okay, here's -1. And I'm going to make this up. There's -2, there's 0. If I'm taking numbers that are slightly smaller than -1, I'm looking at numbers like, say, -1.1, -1.01, -1.001, right? This would be from the left. And then if I'm approaching from the right, I would take numbers that are slightly larger than -1, like -0.9, -0.99, -0.999. Okay, so what I'm going to do is I'm going to evaluate the function at some of these values so that I can see what's happening with my graph. Okay, so let's do this part here. Okay, let's go with, let's see, what numbers we're using. Okay, let's try -1.1. Let's see, we got -9. Okay, so we're going to do this again. Y bars, function, the third one. Let's try -1.01. And I'm looking for a pattern. Okay, so look at what's happening with my numbers. My numbers are growing in the negative direction, right? So I'm getting, remember, these are like my y values. I'm at y -9. Now I'm at y -99, right? My guess is the next one is going to be even smaller, right? So if I now type in -1.001, my guess, -999, there we go. Okay, so as I'm coming in from the left, we are approaching -infinity, right? We're approaching -infinity. Now let's see what happens as we take the limit as x approaches -1 from the right of f of x, okay? So remember what the values I'm going to be using now. I'm going to be looking at these values, okay? So let's come back to our vars. Let's go to function, third one, and let's type in, say, -0.9. Okay, well, 11. Okay, let's try y bars again, function, third one, -0.99, 101. Okay, so what's going on with my y values? They're growing larger, right? They're getting bigger. Let's try that one last time. I think you guys can probably tell what's happening, but let's just confirm this. -0.999. Oops, I forgot my parentheses. Second insert, parentheses, there we go. Close that off. There we go. Okay, so you can see these values are growing larger, so this is going towards positive infinity. So what kind of discontinuity would we have? We would have an infinite one, right? You can see the numbers are growing either large in the negative direction or large in the positive direction, right? They're growing without bound. Okay, so now let's talk a little bit about continuity over an interval. So we've talked about continuity at a point. Now we can extend this to continuity over an interval. So we're going to develop this idea for different types of intervals. It might be useful to keep in mind of the intuitive idea of a function continuous over an interval is we can use a pencil to trace a function between any 2 points on the interval without lifting the pencil from the paper, right? That's what I talked about before. So it says a function is said to be continuous from the right at a if the limit as x approaches a from the right is equal to f of a. And a function is said to be continuous from the left of a if x approaches a from the left of f of x is equal to f of a. All right. So now we're going to talk again about continuity over an interval. So it says state the intervals over which the function f of x is equal to x minus 1 over x squared plus 2x is continuous. Okay, so like we said before, we have a rational function. We're going to take the bottom portion, y'all, and we're going to set this equal to 0. So we can factor this thing out, and we're going to end up with two values, x equals 0 and x is equal to negative 2. These are the values for which the function is not defined, right? Because it makes the bottom part 0. Okay, so I'm going to draw my number line here. Okay, the two numbers that I'm really interested in are negative 2 and 0. Okay, so remember, in terms of my number line, over here to the left is negative infinity, over here to the right is positive infinity. So let me see, I think I could probably do it like this. So I'm going to try to make like a little circle right here and a little circle right here, because in terms of my x-axis, I'm going to have, I can't use those values, right? So where would this thing be continuous? It would be continuous as we come from negative infinity to negative 2, and then we're continuous again from negative 2 to 0, and then we're continuous again from 0 to infinity. So what that, in essence, what that means, y'all, is that when we're looking at the graph, right? If we're looking at the graph of this function, we can, the graph is going to, you're going to be able to draw the graph on the left. So anytime you're to the left of negative 2, you should be able to draw the graph without taking the pencil off the paper. Between the x values negative 2 and 0, you would be able to trace the entire graph between those 2 points without having to take your pencil off the paper. And then anytime from 0 to infinity, you'd be able to look at the graph or trace the graph without having to take your pencil off the paper, right? And this is what we mean by being continuous over particular intervals, okay? Let's see. We have something here called the intermediate value theorem, okay? So I'm going to explain, by looking at the picture, y'all, I'm going to tell you what the intermediate value theorem says. Okay, this is in essence what the intermediate value theorem says. If you have these two x values, right? One of them is a, one of them is b. And you find the value of f of a, and you find the value of f of b. As long as our function f is continuous, then if you find a number on the x-axis, c, that's somewhere between a and b, then when you find the value of f of c, that value is going to be somewhere between f of a and f of b. So if c is between a and b, and the function is continuous, then f of c is going to be somewhere between f of a and f of b. That's what the intermediate value theorem basically tells me, okay? But the function has to be continuous, okay? It has to be continuous over that interval, over that closed-bounded interval from a to b, okay? Can't be discontinuous there. Okay, so now let's take a look at what we have here. It says, show that f of x, which is equal to x to the third minus x squared minus 3x plus 1, has a 0 over the interval, closed interval from 0 to 1. So the first thing we're going to do is we're going to say, well, what's f of 0? which would mean we're going to take 0 to the third minus 0 squared minus 3 times 0 plus 1. All of that is equal to 1. Okay, now let's find f of 1. So 1 to the third minus 1 squared, minus 3 times 1 plus 1. What is this equal to? Let's see. 1 minus 3 plus 1. That goes away. Negative 3 plus 1, negative 2. Okay, so what we know is that f of 0 is equal to 1 and f of 1 is equal to negative 2. So that means that somewhere between 0 and 1, if we pick a number a that's between 0 and 1, it's going to be equal to 0. Okay? So let me kind of show you roughly what I'm talking about. So I'm going to draw a very rough sketch of my graph. Okay? So here's x equals 0. Here is x is equal to 1. So at 0, we were at positive 1. At positive 1, we were equal to negative 2. Okay? So here's the value of f of 0. Here's the value of f of 1. The function is continuous over this interval, which means I can connect, there we go. When I connect these 2 points, I'm going to be able to do it without taking my pencil off the paper. So what does that mean? I don't know what it's going to look like, but it's going to do something like that, so that somewhere in here, there's the value a, so that f of a is equal to 0. That's what the intermediate value theorem tells me, okay? Alrighty. Now, let's take a look at this next one. It says f of x is continual over the interval from 0 to 2. F of 0 is greater than 0. So what does that mean? It just tells me that f of 0 is positive. F of 2 is also positive. Can we use the intermediate value theorem to conclude that f of x has no zeros in the interval between 0 and 2? Explain. Okay, so look, I'm going to do this. Here's my x-axis. Here's 0. Here's 2. It says f of 0 is a positive number, so maybe it's right there. I don't know. F of 2 is also a positive number, so it's up there. Can we say it's that we're absolutely not going to have any zeros? We can't necessarily say that, y'all, because the graph could do something like this. It's still continuous, right? I mean, is it possible? Yeah, I could do something where the graph does that, but it doesn't mean that I can't draw this particular one, right? So no, we cannot guarantee. My answer would be no. Why? Just look at the picture. It's right there, right? Alrighty, let's take a look at this next one. It says for f of x, which is 1 over x, f of negative 1 is equal to negative 1, which is less than 0. Yes, it's a negative number. And f of 1 is equal to positive 1, which is greater than 0. Yes, it's positive. Can we conclude that f of x has a 0 in the interval between negative 1 and 1? Okay, so we're looking at the function f of x is 1 over x, right? And we know that f of negative 1 is equal to negative 1, and f of 1 is equal to positive 1. So they're saying, can we say now that we have a 0? So again, I want you to kind of think about what's going on here. Say here's x is negative 1, here's x is positive 1. And if I look at my graph, right, I know that at negative 1, we're down here, and I know at positive 1, we're up here. Can we say that we're now going to have a 0 in here? And the answer would actually be no. Why? Because if I look at f of x to be 1 over x, and I'm looking for over the closed interval between negative 1 and 1, the function has to be continuous over that entire interval. And you know what? If we try to find f of 0, this thing here is undefined. So can we? No. The function has to be continuous over the entire closed interval, And in this case, it's not continuous. Okay, it's not continuous. The graph does something like that, and the graph does something like that over that interval. Okay. Alrighty, so now let's take a look here. It says the graph below is a function f of x. Again, y'all, I took these problems directly from your homework. Let's see, determine which one of the following rules, determine which one of the rules for continuity is first violated. Okay, so number one, is f of a defined? Can we find f of -1? Yes, we can, because we have a solid point there. That's true. Okay. Does the limit exist? Remember, in order for the limit to exist, the limit from the left has to be the same thing as the limit from the right. The limit does not exist, right? My limit from the left exists, my limit from the right exists, but because they're different, the overall limit doesn't. That's the one that's violated. Okay. All right. Same thing here. Determine which one of the following rules for continuities first is violated at x equals 2. Is f of 2 defined? Can we find f of 2? We cannot. It is not defined. That's why that rule is being violated, right? It is actually undefined. Okay. All right. So now let me take a look at this one. This is a pretty rowdy graph here. Okay, so it says the graph below is the function. Okay, so there it is. Okay. It says, select all statements below with which you agree. You may be checking more than one box. Okay, so let's take a look. Is f of 1 defined? Yep, we got a solid point. I'm checking that one. Does the limit as x approaches 1 exist? Well, the limit from the left exists and the limit from the right exists, but they're not the same. So I'm not checking the second one. Okay. Does the limit as x approaches 3 from the right, is that the same thing as f of 3? So f of 3 appears to be 1, and as I take the limit as I approach 3 from the right, it's also 1. That one is true. Okay. So let me clean up my little mess that I've done here. Okay. Is the function continuous at 3? No, it isn't. It's not continuous at 3. The function is not continuous at x equals 1. That is true as well. So those would be the 3 boxes that I would check on this particular problem, okay? All right. So now let's take a look at this next one here. It says let f of x be equal to 5x plus 10 if x is smaller than 2 and 24 minus 2x if x is bigger than 2. Okay. So let's see. I want y'all to notice f of 2, is it undefined? Notice this is telling me to use the top part when x is smaller than 2 and use the bottom part when x is bigger than 2. So it's not actually defined at f of 2, okay? If I were to find the limit, so I'm already going to check that one. If I were to find the limit, if I were to plug in a 2 in here, that would give me 20, that's true. If I were to plug in a 2 on the bottom portion, that would also give me a 20. So the limit does exist. The limit is fine, right? And I would probably pick this one as well. I don't know. I don't know if I can pick it. I know definitely it's not undefined. I mean, it's undefined. So I can't do the first one. That's why I'm selecting the first one, because it's not continuous, because f of 2 is undefined. And if f of 2 is undefined, then the limit can't be equal to the same thing. I'd probably check them both. Okay. Alrighty, let's take a look, see at the next one here. Let f of x be equal to 5x plus 2 if x is smaller than 4. 45 minus 5x is x is bigger than 4, and negative 2 if it's equal to 4. So number one, we do know that it's defined at x equals 4. So this part, I can't check the third box. I can't check it because it is defined. Okay, now let's see if the limit exists. So if I were to plug in a 4 in the top part, so 5 times 4 is 20 plus 2. So the limit as x approaches 2, as x approaches 4 from the left would be 22. Okay. If I find the limit as x approaches 4 from the right, I'd be plugging it in right here. which would be, let's see, 5 times 4 is 20. 45 minus 20 would be 25. The limit does not exist. Okay? The limit doesn't exist. So that's my choice right there. Alrighty, let's see if we got any other ones here. Oh, that appears to be it, y'all. Okay, so this here was 2.4. Hope it makes sense.